let's get started. I'm gonna go quickly through what we have done so far. So we started with this paper, Neural Machine Translation, which had everything in it. It was defining the problem for us when it comes to inference. Then we introduced recurrent neural networks, in particular gated recurrent neural networks, and we were using them. And then we introduced attention as well. This was for modeling this probability. Once you know the probability, you can write down your likelihood. And once you write down your likelihood, you can maximize it. So the training data is in the form of source sentences, target sentences. You train your algorithm. Now it's time to evaluate it. And we introduced a blue score. It's not a perfect score, but it's the score that you usually use in practice. But then we said, let's forget about attention for a while and just focus these sequence models. Focus on the recurrent neural network, the encoder-decoder approach, and try to use them. So we try to use them for sequence-to-sequence learning, in particular translation, machine translation. And we said it's not going to do a good job on its own, but if you use that, if you use your neural network to rescore the recommendations or the translations that are coming out of your baseline system, your statistical machine learning framework, then you're going to get some improvements. But on its own, it's not enough to beat the state of the art. Then we said there is another way of doing it. We can add these scores that come out of a neural network and add them as additional features to whatever hand engineer features that you had already for your statistical machine translation. And yes, these are independent. And because they are independent, they are going to add more information. And therefore, you manage to increase the performance of your statistical machine translation this way. But again, neural networks on their own were not able to give you good translation. Now, this paper came along. Not only it introduced a new architecture, so there is nothing special about this architecture. It's telling us that the encoder, we can replace it with CNNs. So that's cool. But it made two observations that's going to help us a lot. It says that maybe the sentence length matters. And the other observation is that the vocabulary size matters. So the sentence length matters, and this is proof. If you increase the sentence length, the quality of your translation goes down. If you believe that the blue score is a good score, and no matter the architecture, whether you're using RNN encoder or this gated recursive CNN encoder. And in terms of vocabulary size, if there are more unknowns or unknown words in your sentences, then the quality of the translation goes down. So these two observations matter. Then we go to the next paper, and it's going to try to address the sentence length. And the paper after that we're going to cover is going to try to address the vocabulary size. So we stopped here last session. So we had this LSTM, stacks of LSTM. It was encoder-decoder architecture. All we need to model is this probability of the output sentence given the input sentence. Y is the entire output sentence. X is the entire input sentence. This is our sentence. We have done it multiple times by now. This is the target sentence. They have different length. Then you write down the log of your probability. And if you manage to do that, the rest of it is optimizing this objective function, maximizing this or minimizing the negative of this. And there is nothing wrong with this objective function. So given the source sentence and the previous words that you already translated, predict the next word. So that's our source sentence representation. We usually write a model for G here because the dimension of the hidden states from these hidden states that are coming out of LSTM is usually different from your vocabulary size. So you have to adjust the size. You do some projection, matrix vector multiplication, and then you do softmax to turn them into probabilities. We can have recurrent neural networks of various forms, RNNs, GRUs, LSTMs. But once you do that, you can write down your objective function. You have pairs of input-output sentences in your training corpus, and then you try to minimize this. Once the objective function is minimized, you have good parameters. But the focus of this paper is trying to address the sentence length. And they said, maybe attention. We need to bring back attention. Maybe that's going to help us address the issue with the sentence length. And there are different versions of attention that this paper is going to introduce. And we're going to try to study all of them. First of all, what is this G function? This G function is coming out of a matrix vector multiplication. I need to tell you what is H tilde. H tilde is a tan H applied on a matrix multiplied by two vectors. H is the target hidden state. So there is a target hidden state here. And then there is going to be a source side context vector. And this source side context vector is going to be dependent on the word that you are translating. So this is very similar to the attention framework that we introduced before in the first slide. Rather than it being a single vector, it's a vector that is time dependent. And we know that CT is going to be a linear combination of the hidden states of the source sentence. And we have an attention budget of 1, and we are spreading it among all of these hidden states, and that's going to give you CT, okay? But the focus here is trying to come up with different types of attention mechanisms. For attention, you're going to have a budget of 1, therefore you're going to use a softmax. You can call it a line, you can call it attention, whatever that you call it, it's going to be a budget of 1 that you're spreading among your source sentences. So the question is, what is H bar S now? H bar S is the source hidden state. So you have a target hidden state and you have a source hidden state. And these two are paying attention to each other. How much attention should this, at this point in time, while predicting this word, should we pay to the rest of the input sentence or the hidden state of the input sentence? But up until that point, we knew about it. It's all about this score. How are you going to score? If I give you a pair of target hidden state and a source hidden state, how are you going to come up with this attention? And there are multiple versions. This version we saw. So you first concatenate HT and H bar S. You multiply them by a matrix. This is equivalent to having two matrices and multiplying them separately by HT and H bar. But then you can concatenate and then write them in one shot. You push it through tanh, and then you introduce some new parameters. Because this is a vector, you want to turn it into a score. It has to be a scalar. So you do a dot product. And this we saw before. There is another alternative. You know HT, you know H bar S, just form the dot product of the two. And this is the cosine similarity between the target and the source hidden states. And there is a general formulation. So it's generalizing the dot product. You first multiply by a matrix in the middle, and then you do your dot product. This is the one that is going to survive. And we are going to use that later on when we do transformer models. So this is the one that's going to survive. But different types of attention mechanisms were around, and we are seeing different versions today. There is another version, and this version says, don't pay any attention to the source sentence. Just take whatever the outcome of the hidden state at this time is, multiplied by a matrix, do a softmax to turn it into numbers from 0 to 1. They add up to 1, and then that's going to give you 80. So this 80 is not paying any attention to any of these source sentences. So that's another version. Visually speaking, this is what is happening. For the global attention model, you have HT tilde, which is here, and this is the one that's going to give you the probability of your word that is being outputted. So your word could be any of these in your sentence. That is HT tilde. HT tilde is going to depend on CT and HT. So it's going to depend on CT and HT. Pairs of HT and H bar are going to give you your scores. And once you know your scores, they are going to give you your attention vector. So it's going to give you a global attention, and this is going to add up to 1. It's going to be a vector that is going to add up to 1, its elements. And then to form CT, you're going to take an input from here, multiplied by this vector, another input, another element multiplied by this vector, add them up all, and that's going to give you CT. So we know how to form CT, we know how to form AT, we know what is HT. They are coming out of these red boxes. And then in the end, you're going to do your prediction. So is everything clear with global attention?
I just had one question about the index T. Is it it's like H1 and then H2, H3, and so on, and those would be the four blue boxes. The target, or no, target hidden state would be other way around, the red hidden boxes. But indexed by like 1, 2, 3, 4. T is like a time index.
Yes, so it's going to go 1, 2, 3, 4. And that's when you're predicting the first word in the sentence, the second word in the translation, the third word in the translation. So T is counting that.
And then S similarly would be like source 1, 2, 3, 4 for the blue ones.
Yes, exactly.
Okay.
And then the question is, at this point in time, when you're outputting this word, to which words in the input sentence are you going to pay attention to?
Mm-hmm.
And how much attention are you going to pay to each one of these hidden states? Any other questions?
The other question I had is if the attention is a distribution over words or a distribution over previous hidden states.
It's over the hidden states that are coming out.
Yeah, that makes more sense. Yeah, perfect. Thank you.
Okay. For this model, it's for the hidden states. We're going to expand on that. But the point of this paper and why am I going through it is that you can have different models for your score. People started with this concatenated version, but then you can have the dot product and the general or no attention at all, or local attention. You pay attention to yourself. You can expand upon that local attention. Why are we doing this? Because if you want to pay attention to everybody else in the input sentence, it's going to end up being costly. To reduce the cost, maybe you're going to say, I'm going to only pay attention to a particular portion of the input sentence. This is going to be a little bit tricky to explain, but if you are a little bit patient, things are going to become clear. So you're now sitting at this point in time. You can think of it as time, you can think of it as index, or you're sitting at this point and you want to predict this word. Maybe you're here and you want to predict y. And you want to know, where should I pay attention to? First of all, and you want to do it locally. First of all, you're going to say, I'm going to have a P of t that is going to tell me where in the sentence I'm going to look at. So maybe you're going to look at here. Maybe that's your PT. That's the value of your PT. And then around that, you're going to create an interval of maybe one word to the right, one word to the left, or two words to the right, two words to the left, and pay attention only to those 5 words or 3 words. And then your attention is going to be 0 everywhere else. So the question is, how are we going to model this PT? And this is exactly what I just mentioned. As soon as you know PT, you know your interval. And once you know your interval, you can pay attention to that interval locally. And then the rest of the sentence you don't pay attention to. So the question is how we're going to model PT. Still, your attention is going to be the same as before, but now it's local. Okay, rather than AT having the size of the entire input sentence, AT is going to have a size of 2D plus 1. And then the rest of it is zeros, so you don't need to do extra computations. One model is that PT is equal to T. Just set it to be T. If you're translating the 4th word in your target sentence, just go in your source sentence, look at the 4th word, and then create an interval around it. That's one model. This is called local M. Another model is that you can have this PT to be a learnable function. Maybe there is not a one-to-one correspondence between words in the target sentence and the source sentence. Maybe it's better to do a predictive alignment. Okay, let's say you have capital S, and that's the size of your entire source sentence. That's the length of it, and that's capital S. What you can do is you can parameterize. If you multiply S by a number that is from 0 to 1, and then you quantize it, because in the end, you're going to need integers. These are integers, 1, 2, 3, 4, 5, etc. If you multiply that by a number that's from 0 to 1, it's going to tell you where you need to pay attention to. Maybe the length of your sentence is 1, 2, 3, 4, 5. If you multiply 5 by, let's say, 0.5, that's going to give you 2.5. And then you round it, and maybe you round it down, and then you're paying attention. Your PT is going to be 2. But then the cool thing is that you can make this depend on your hidden state, on the word that you're translating. So you can say HT, you're going to multiply it by a weight, you're going to multiply it by a 10H, and then because in the end you need a scalar, you're going to multiply it by a vector. It's going to be a dot product. It's going to give you a scalar from negative infinity to positive infinity. You squash it through a sigmoid. It's going to make this a number from 0 to 1. And now this is a learnable aligned position, so you can learn it. And once you know PT, regardless of how you do it, uh, the rest of it mathematically is going to look like this, but on your computer, you don't need to pay attention to everything in your source sentence. But what are we doing now? We still have this alignment of HT and H bar S, and that's exactly what you have up there. But then your alignment is going to go exponentially fast to 0. So this is an exponential function. It goes, it's like a Gaussian distribution. It's 0 and then suddenly becomes non-zero and then becomes 0 again really fast. And then you can set the standard deviation of this to be d over 2. And this is basically paying attention to the words that are close to your aligned position.
Can I ask real quick? It seems like the global attention is just a more general form, because it's possible that you could, in the global attention like framework, you could end up just paying attention to, say, one position.
Yes, so you're absolutely right. The global attention model is a better model compared to the local one, but it's always a trade-off. It's a better model, but in the end, it's more costly
Just
because you
more for
have,
like learning time.
yes, so it's a more costly because you have to pay attention to everybody in the source sentence, and these source sentences could be really long, okay? So you're trying to reduce the cost from the size of your source sentence S, which could be large, to something that is deterministic. It's 2D plus 1. It's always that number. We're going to talk about the cost of attention models. So they're good, but they are not perfect. Okay, they have their own drawbacks. They are costly.
One last question about this. Like the main difference is the locality, and so that would just change. Like WP would output something that's 2D plus 1 big versus the WA matrix above would give you something that's as big as your sentence, input sentence.
So you still have this WA.
Oh, that's right.
That is still present because you have this alignment. Okay.
Yeah.
You still have WA. You have more parameters here. But then you have your attention, but you manually force it to be 0 exponentially fast. It's only non-zero around that local point that you're interested in. Okay, any other questions? So you can have different types of attention mechanisms. And locally, this is exactly what is happening. You have, you still have HT tilde. It's going to depend on CT and HT. The question is how are we going to now compute CT? So, and how are you going to compute AT? First of all, you're going to take HT, you're going to multiply it by a matrix, you're going to multiply it by another vector, push it through sigmoid, multiply it by S, that's going to give you PT. So now you know PT. PT is going to tell you this location here. Okay, perfect. So now that you know PT, you can go one word to the right, one word to the left. This is one word to the right, one word to the left. And then from that, you can compute your attention. So now you have an attention span of 1, and you're spreading it among 3 words rather than the entire input sentence. Okay, once that's done, you have AT. Now CT is going to be AT multiplied by these vectors. So you have an attention span of 1 that you're spreading among these vectors. That's going to give you CT. So do you see the difference? Here, CT is going to depend on everybody else. In the source sentence, this is going to depend on the words in a local fashion. So it's local. There is another trick that I want you to learn, and that's input feeding. This happens a lot, and this is going to improve the performance of your machine translation. So whatever hidden state that you end up with right before doing your translation, this is H tilde, you take that and push it as input to your LSTM, the next LSTM unit. Not only you input the word, but also you are inputting the hidden state. That's called input feeding. That's going to increase the performance. So what happens after all of these? Which model are we going to use? Are we going to use global attention or local attention, and which one is the best? First of all, you can look at the perplexity. So we're gonna talk about perplexity when we do language modeling. So you can have a perplexity for your translated sentences. And for perplexity, the lower is the better. So it turns out that this local P general is doing the best. So general is this general attention type here. And local P is this predictive alignment model. And it's giving you the best blue score. For blue score, the bigger is the better. And don't worry about unknown, because there are some ways to deal with unknown words in your sentences. Maybe a simple solution is that if you encounter an unknown word in your test data, just copy it from your source sentence to the target sentence. Maybe the output here is an unknown, but then you just copy it from B. So you copy B and put it here. That's one way to deal with the unknown words. Okay, that was the story. But if you remember, we started this slide with a question. And the question was this: we want to address the problem of the sentence length. And we had this observation that the blue score is going to go up, and then it's going to drop and get lower as you increase the sentence length. So this is the observation from the previous paper. It turns out that attention, all of these other models have attention in them. It turns out that adding the attention is going to fix that. It's going to address that. Okay. Any questions before I move to the next topic?
I just had a quick question. The local attention model has, it looks like it has more parameters overall, but it just has to consider fewer source hidden states.
Yes. So you have more parameters because of computing this PT.
Okay, thanks.
And there are two versions of it. One of them adds no more parameters, and the other version is adding some parameters.
Okay, yeah, I see that.
But the computational cost is lower, much lower.
So is it the case that you only do this like this Gaussian weighting on the alignment score for the locations S that fall within the aligned position window?
This is actually a mathematical way of doing it. And this is exactly the question that we had from what happens if you are rounding PT to its nearest integer? How do you differentiate through it for learning? This is what you do for you to be able to differentiate through your attention mechanism. Okay, you can keep PT to be 2.5, and then you do your training this way. But once you do your inference, you do that quantization. So this is just a mathematical formula for you to be able to differentiate and then write it in a nice way. But once the training is done, you don't need to compute to pay attention to the things that are outside of this exponential.
Okay, so everything that's, well, I guess my question then is like outside the exponential, exponentials are never exactly zero. So is it that we're paying infinitely small amount of attention to all the words, or do we?
Mathematically speaking, yes, but in practice, you just set them to be zero.
You just truncate it when it's outside the window.
Yes, because you don't want to do extra computation.
So you take like a Gaussian and then just chop it off on the left and the right tail when it gets outside of that plus or minus D window.
Exactly, yes.
That makes sense. Thank you.
Okay, perfect. And Matthew, does that answer your question? And how do you differentiate? Okay, perfect. But the observation is that attention is important. And it's important because of dealing with this sentence length.